Second video, but first one on calculus for our, what are we? We'd be in section 2.6 if we're in the Stewart text. We're going to talk about the limits at infinity and how they tie in with horizontal asymptotes. So we look at what's in yellow. That limit as x tends to infinity of some function f of x. We say it's tending towards some L. And of course, your text word's a little different. I'm a little loose with my language, so don't listen to me. We should probably read these definitions of what a limit is. Oh, shoot. Well, it says let f be a function defined on some interval from a number up to, okay, it's got to go all the way to infinity. It means the domain's got to go all the way up to positive infinity. It doesn't matter where you start, just it's got to go all the way. The x values have to go to infinity. So then it says as the x values get as large as you can possibly think, all the way to the right of a graph, so much further to the right of the graph than you could ever think. We're talking next town over and then go to the next world over. We're going that far to the right. And we want to know, so it's saying, where is the function tending towards? Now, if it goes to a number, not infinity, but a number, that's saying it's not going to blow up. Like this one off on the right. You're like, hey, look. As your x values get bigger and bigger and bigger, it's getting closer and closer to that line, y equals L. It's a horizontal asymptote. It's saying as your x values get bigger and bigger, if it actually goes to a number, or function goes to a number, or a limit goes to a number, well, you must have a horizontal asymptote there. Whack, look at these things, huh? And then horizontal asymptotes can cross over themselves. It's just where it's tending towards. As that x gets so infinitesimally large, we're saying, hey, if it goes somewhere, that's a horizontal asymptote. Now, typically we get those from rational functions. Remember rational functions? If you watch the previous video, then you're like, yes, I know what a rational function is. Maybe you don't remember from college algebra or pre-cal, something like that. I'll give you an example of one. Oh, here it is. Rationals. Think fraction. What's the degree of the top? 0. What's the degree of the bottom? 1. So that's telling us we must have a horizontal asymptote at 0. Have we ever graphed this thing? I can't remember if we have or not. I'm kidding, I'm being facetious. So there we go. There's our y is equal to 1 over x. And we go, all right, cool. So as x gets really, really big, that means to the right. As our x's go towards infinity, we go to the right. What's the height? You're like, bro, it's getting close to the x-axis. The x-axis is just y equals 0. That's what the x-axis is, this little line right here. That's y equals 0, the x-axis. Y-axis, that's x equals 0. Cool. Cool. So we can say, since that's the horizontal asymptote, the limit as x tends towards infinity of 1 over x is just 0. Neat. Neat. What do you think's going to happen if I change this and went, nope, ha-ha, ha-ha. It's x squared now. I'm sorry. It's x squared. Now it looks like this. What's the answer? Yeah, it's still the same frickin' thing. Oh, shit, I made a mistake. It's actually the 22nd power. There's this, it's the same graph. It's the same fricking answer. Oh. Oops. Another mistake. I can't stop making these mistakes. The 221st power. Oh, since it's odd, it's going to go look like this. It's still going to frickin' 0. It's still going to 0. Are you catching my point? Are you catching my point? All right. But what do you think happens with this? Let me just see. Uh-oh. I'm kind of letting it go here. What happens as our x values get small? Go the other way. Go this way. What happens when they go to the left? What happens as our x values go towards that negative infinity? Well, if our function gets arbitrarily close to that value of L, it has a horizontal friggin' asymptote there, then that's going to be the value because it's getting infinitesimally close. As long as we make x sufficiently large negatively, or negative. Ugh. Yeah, big old fancy words. We're being like, dude, where's it approaching? Where's it going towards? So for our answer here, for my funky function that I was making up, that 1 over x to the 221st, we're going to say, well, the limit as x tends towards negative infinity of 1 over x to the 221st. Well, that's still frickin' 0 too, huh? I got a graph there. You can see it. It's heading that way to the height of y equals 0. And this really just opens something up to us. This is the hookup. This is how we're going to solve the rest of them. Where you might know the answer to some of these problems, but you're still going to have to kind of play a game with me. And here's the big oomph that pops out. So as long as the exponent is positive, not negative, positive, and I still don't know why, but it needs to be a rational number. So like a fraction, like 2/3 is cool, 4/3 is fine, 7, 1. But it can't be like pi. It can't be e. Irrational numbers, the exponent can't be one of those. I don't know why. I don't see why that would be an issue, but I don't know a lot about math. I only know a little bit. I should ask the internet one of these days. It'll tell me. All right, going back into it. But it says as long as you've got 1 over x to any frickin' number that's positive, and that x is tending towards infinity, it's going to 0. And it doesn't frickin' matter if it's a negative infinity either. Didn't I just show something like this? I was just playing around with these numbers, and I just kept changing it over and over and over. But the answer just stays the damn same. So this is going to be the game that we play. This is our game. So let's jump into it. Let's see what happens. So we're going to always want to create these in our problems. We want to create these. Well, I don't know about in our problems, but let's go. Let's see one done. So let's go evaluate this limit. The limit as x goes to infinity of 7 over x squared minus 1. Where's that going? Well, just by looking at it, I will tell you the answer is 0. The degree of the bottom is larger than the degree of the top. Do you see that the degree of the top is 0? There's no x's up there. The degree of the bottom is x squared. That's the same thing as 1 over x. As limit as x goes to infinity. It doesn't make any freaking difference, but this is how we're going to solve these. We want to look at the bottom and go, what's the degree of the bottom? And whatever the degree of the bottom is, we're going to say we're going to multiply top and bottom by 1 over that. The x squared. 1 over the x squared. And even if you know the answer, you're like, it's 0. I might make you write this shit down. I'll bet you I can trick you if you don't play this game. So, as we bring it in, this might be a little bit weird for you to see, but it's the limit as x tends towards infinity. Now we got our 7 up top and our x squared minus 1 down below, but we're creating more fractions. I know typically that's not what we want to do, but that's going to go underneath here, x squared, and this one's going to go underneath both of these. But I don't like the way I just wrote the bottom. That's too much work. I know how these things operate. Why wouldn't we just do this instead? Just put the x squared underneath each term. Now let's clean it up. And this might be long-winded and you're like, oh my gosh, I already know the frickin' answer. How come I'm doing this? Well, so we can learn stuff. So what's x squared over x squared? 1. Now, if we were to use our limit laws, I don't require that we do this. I don't think we need to bring our limit in and go limit as x goes to infinity of 7 over x squared. I'm doing it in red to show you, like, don't do this. Don't do this. Oops. Going to infinity of 1 minus the limit as x goes to infinity of 1 over x squared. So instead of writing all this out and then solving it out individually, you can do this. So 7 over x squared, that's that rule. That's that law. It doesn't matter if there's a 7 out front. So any number over x squared, we should change this to just say any number a. Any number a. It doesn't make any difference what freaking number, because you could bring the constant out to the front and just have it as, oh, oops, this is just going to be, you take the a out and go, oh, I'm bringing it out to the front by factoring it. That'd be the same thing, right? And what's a times 0? 0. I don't know if that made any sense, but basically, the top is going to 0. 7 over x squared, just this, that goes to 0. The limit as x goes to infinity of 1. 1's a number, that just stays there. And then this, we're going to subtract out 0. So we got 0 over 1. But I had to keep going to make sure we got a number down below, because if we got 0 over 0, that doesn't tell you shit. That tells you nothing. So since we got 0 over 1, this does equal 0. Now let me show you how to do it the fast way, where you don't have to go through all this. Once you get to this point, you go like this. That's 0, and that's 0. So now you have 0 over 1 minus 0 is equal to 0. Done. And that's how we'll solve this. All right, in the next ones, we'll actually do some more interesting ones. We'll start talking about the different cases. But this is just a beginning. Get you used to what this notation means. And we'll start dealing with a lot more problems. I think I got about 9 of them for you. So probably do about 4 or 5 in the next and 4 or 5 in the one after that. So I'll see you.